So we're going to look at today is a particular type of belief network called a Markov chain. So here's a picture of the Markov chain. It's just a chain, it's a belief network that's a chain, and often we consider that it keeps going to the right. Right, so it just keeps going here. Okay, so if you think about what needs to be specified in here, for each variable, it needs to specify this given its parents. So it needs to specify S0 given its parents, so that's just the probability of S0. It needs to do the probability of S1 given S0, S2 given S1, S3 given S2, and S4 given S3. So you can just read that off just by looking at this belief network. You know what probabilities need to be specified. So that is, it's the probability of S0, which specifies the initial conditions, and the probability of Si plus 1 given Si specifies how the states change. So it's how these S's change. It specifies the dynamics. So the independence assumption here, if you think about what the independence assumption means, well, let's look at S3. Well, it says that here are all my predecessors, right? But they're all independent given just its given S2. So S3 is independent of it, all the previous ones given S2. So that's what this says. The probability of Si plus 1, given all the predecessors, only depends on the previous one. Okay, so Si is enough information to produce Si plus 1. And often this is S of t is the state at time t. And the state now, this encodes all the information about the past that can affect the future. So Si and so all of these other ones, all these other predecessors are not relevant if we know Si. So we don't need to know those. If we know Si, everything else is, all these other ones are irrelevant. They don't provide any more information. And this is a good definition of what state is. So a state makes it is if you knew this state at one time, all information, the past doesn't affect the future. So if you knew S2, so if you knew S2, everything that's beforehand doesn't affect the future, which is all the way on to the right here. Okay, and often we say that as the future is independent of the past given the state. Okay, we're going to look at a special type of stationary Markov chain called a stationary Markov chain. And what this says is, if you look at here, is that for every I and I prime, the probability of transition is the same for I as it is for I prime. So this doesn't know, it's not like this, the probability of how S7 depends on S6 is the same as how S27 depends on S26. Okay, so it doesn't actually depend on the time. So that's what we're going to mean here. So stationary means it doesn't depend on the time. Okay, so that we're going to assume that for this one, the Markov chain is stationary. This is a very common assumption we'll make. And this go back. So now what we need to do is now we need to specify two things. We need to specify the initial state, probability of S0, and this one conditional probability table of how Si plus 1 depends on Si. So this is a simple model. It's easy to specify, and it's a natural model. So what we're going to do is if something depends on the time, we're going to include that as part of the state. And this network can extend indefinitely. So once we have one of these, we actually have infinitely many random variables because there's one for each time into the future. Because that's a stationary Markov chain, and we're typically going to assume that. Okay, now a distribution is a stationary distribution. So stationary means it really doesn't depend on the time. If for each state, the probability that you're in some state at some stage I is the same as it is in I plus 1. So the probability of being in little state S is the same for time I and the next time. So the probability of being in S doesn't change through time. So that's what a stationary distribution is. So the probability does not change through time. So every Markov chain has a stationary distribution. That's an important thing to know. So Markov chain is this ergodic. It's a funny word here, ergodic. If for any two states there's a non-zero probability of eventually reaching S2 from S1. So eventually can reach any state from any other state. So not all Markov chains are ergodic. Lots of them are not ergodic. But we're going to define something we're going to use for ergodic Markov chains. So when there's lots of probability chances of getting things, and things are typically ergodic. So if things are noisy enough, it's typically ergodic. So a state in the Markov chain is periodic if there's a temporal regularity visiting the state. So if we think properties about the days of the week, right? Monday always follows Tuesday, and Tuesday always follows Wednesday. or the other way around. Mondays followed by Tuesdays followed by Wednesdays. So there's a period of 7 days. So there's a period. So this is a period of n if the difference in times with visiting a state is divisible by n. So if something happens on Mondays, and then part of the state is the day of the week, then a state that contains Monday, and another Monday has to be divisible by 7. So this is how we're going to do it. So Markov chain is aperiodic if all states only have a period of only 1. So if all states only have a period of 1. Okay, so now why we introduce these two things, it turns out that if it's a Markov chain is unique and periodic, it has a unique stationary distribution. And we can actually compute this stationary distribution just by running this Markov chain over and over again, and we'll eventually get to this equilibrium distribution. So there's a stationary distribution, and it's the distribution that you reach to if you just keep running the system. It eventually gets more and more, it eventually reaches this stationary distribution. Okay, so as an example of a stationary distribution, this is called PageRank. So the Markov chain, SI, the domain of SI is a set of all web pages. So we're going to have a probability distribution over all of the web pages. And then we're going to assume that we're going to start randomly. We're going to start the probability of being any particular web page is 1 over n, where n is the number of web pages. And then we're going to define this transition probability. So we're at pk, and we're considering how likely is it that we're going to end up in pj. Okay, so we're at pk, we're going to end up at pj. Let's go to this other one here that's we're either going to keep surfing, or we're not going to keep surfing. We're just going to act at a random page. This says we're going to jump to a random page. Okay, so that's what this says. We're just going to a random page. Write a random page. And that's with probability 1 minus d. So we're not going to surf, we're just going to keep to a random page. Now let's look at what happened the other time. So if we're not going to look at a random page, what are we going to do? Well, if pk links to pj, then we're going to do we're going to assume that we're going to do 1 over nk. So nk is the number of links from pk. If it links there, it must have some number of links. So we're just going to assume that when we're at this page with this probability d, we're going to jump to one of the links at random. Okay, so one of the links that pk links to, we're going to jump to one of those pages at random. If it has no links, then we're just going to go to one page at random. So that's what's going to happen here. Otherwise, so if it has links, but it's not one of the linked to, when we're going to keep surfing, we're not going to get to that page. We're only going to get pages that it links from. So this is interesting. So it turns out this Markov chain converges to a distribution over web pages, and this is called PageRank. It was the basis for Google's initial search engine. It was invented in the late 1990s. Brin and Page tried to sell the copyright, to sell the patent to this to Yahoo, I think it was, for $1 million. Yahoo didn't want to buy it, so instead they went and formed their own company, which is now one of the biggest ones. And the way we're going to compute this one is they're going to end up with, it's just going to run it you can just run this Markov chain. They ran it for 52 steps, and that was their value about which are the most popular web pages. And it's based on essentially this random surfer who see where you end up. And this gives this PageRank. Okay, so we're going to talk about a few more applications in the next couple of lectures here.